Here's another example. We'd like to find the center of mass of the solid bounded by the paraboloid z equals x squared plus y squared. Here it is. And the plane z equals 4. That's the thing with the black part there. If the density at each point is proportional to the distance between the point and the z-axis. I'll make a comment before I make you think something isn't so. If I were to draw the x-axis and z-axis and y-axis in proper position, they would be through the center of this paraboloid. See, there's x equals 0, here's y equals 0, and z equals 0. The z-axis should be right through there, and it isn't. The z-axis is back here, the y-axis is back here, the z-axis is back there. I don't know if I can change that with the software and still make it look good. There is a box plot of it that still doesn't help too much because you can't see that the y-axis and x-axis are through the center. So I think I'll avoid that and see if there's any other possible way I could get that to happen. I don't think there is. Well, maybe. I don't think perimeter would be the proper place to put it. No, that didn't work either. So sorry to say, the axis style is going to have to stay in the corner. Or I could say no axis at all, but then we can't see the values for the so I'll go back with the corner. The axes are drawn in the corner, but really they're coming through here, and the bottom, the z-axis, would be right here. So back to our problem. X and y coordinates, center mass, are both 0 from the symmetry of the region, and if the density at each point is proportional to the distance between the point and the z-axis, that means that points that are equidistant from the z-axis are equally dense. So therefore, this is symmetrically dense, if I can coin a new terminology. In other words, what's over here is just as heavy as what's over here, which is just as heavy as what's over here, which is just as heavy as what's over here. So therefore, the x and y coordinates are both 0. Keeping in mind, I can only say that now that I've told you where the x, y, and z axis really are. Okay, so then the only task is to find the z coordinate for the center of mass. In order to find that, I guess we need to find the mass first, and then we need the moment about the xy plane. So the mass first would be the triple integral, and this k times the square root of x squared plus y squared is the density of a particular point, because that's the distance of that point from the z-axis. And so that's pretty straightforward. And the moment, of course, just has an extra z in it. The moment about the xy plane has an extra z in it, and there it is with the extra z in it. So if we switch the cylindrical coordinates, we could say that r is greater than 0, but less than or equal to the square root of x squared plus y squared, which is equal to the square root of z. And then the integral for the mass comes out kind of nice, because this replaces our z, and so we wind up with an r squared there, and r going from 0 to z, theta going from 0 to 2 pi, and z going from 0 to 4. So hopefully you can work that out without too much difficulty. Like I say, that's just replacing this with an r, and our dv is already r d theta dz. And so if you perform this integration, which is it's trivial integration, so I'm just going to say this one is trivial, this one is trivial, and if we divide one by the other, you get 27ths. So a little bit less than 3, and that's a very reasonable answer because we know this thing's a little bit bigger towards the top than it is towards the bottom. So getting close to 3 and saying that our balance point would be up here is very reasonable. Of course, it's down in the center of this thing on the z-axis, so seems like a very reasonable answer.